Hello, this is our first attempt of a vodcast for Extension 1 Mathematics in Year 12, a very important topic called inverse trig functions, and I'll attempt to do this in about half an hour. First of all, to give you a little bit of an idea of what we're talking about, there's two parts of maths which they call pure maths and applied maths, and that's actually what happens at universities too. Applied maths is probably easier. Simple harmonic motion, which they call SMS, projectiles, which is a very important topic in the Extension 1 maths, and a topic which is a bit weirdly named is growth and decay. So that's called the applied maths, and to connect that you need pure mathematics, which is basic calculus, algebra. Simple harmonic motion, you use a lot of trig work, trigonometry. In projectiles you use parabolas. And in growth and decay, we use logs and exponentials. Now, these things here, trigs, parabolas, logs, exponentials, are all functions. And they're the functions that we do in pure mathematics to help us in applied maths. And this is most important to know the linkage. You will be asked questions in pure mathematics, but then the tough part comes in applying these particular areas in the question 6 and 7, the band 6 is over here. If I just come today, we talk about this term inverse trig functions. Now the first thing you've got to know is what is an inverse. I think we know a little bit about trigonometry. What is a function? Now what's an inverse? Okay, now there's three parts of it. There's inverse, trig, function. We all know what trig is, the trigonometry and so forth. Sine, cos, tan, and the sec, cosec, cot, the 6 trig ratios and how we draw those. What I want to do now is what is an inverse? What's the definition of an inverse? An inverse, to give you an example, y equals e to the x, which we know is an exponential, is an increasing curve. The inverse of that function there, the inverse is x equals e to the y. There's an interchanging of the ordered pair. Where you see x, you put y. If you took the y equals, for example, what? Make an easy one, sine x. The inverse of that is x equals sine y. Now that's quite simple. So what does it mean? What does an inverse mean? Okay, an inverse means, graphically, what does it mean? Now I might give a couple of examples here. First of all, if you took y equals x squared, we know, and I'm just digressing for one moment, always label your axis. If you reflect that particular graph in the x-axis, clearly it would look like that. And the equation is y equals minus x squared. Anytime you put a minus in front of a function, in this case x squared, you get a reflection in the line y equals naught or the x-axis. So what is an inverse? An inverse is a reflection, not in the x-axis or y equals naught, but in the line y equals x. Now this is not particularly hard to prove, it's quite easy actually. And what's the reflection without knowing any maths at all? If this point here was, as we know, 0, 1, the reflection on that line there, if you go reflected, this would be 1, 0. It's an interchange of the ordered pair. Now if you say that's 45 and both those angles are equal, and you can see that if this is the perpendicular bisector of that line there and both of those things, that's what you get as the reflection. That's just in one particular point. And the curve looks like, it's asymptotic here, and it would look like so. Now I haven't drawn it particularly well here, but you can see this is 1, 0 and this is 0, 1. I hope you can see that. I haven't drawn it well. That's what they look like. This is the curve y equals x, and this curve is x equals e to the y. Now, x equals e to the y is not a good form to have it in, and they always put it as y equals. And so how do you get y equal to that? Well, the easiest way is to take the log of both sides, and you get the log of x, this is to the base e, and you use your log laws, and that's y equals log x. In other words, y equals log x, or log or log if you want to use that term, or ln, That form there is the inverse of y equals z to the x. Note I've made y the subject, that's another way of putting it. So we've just tried to define what the word inverse was, and I'll just repeat again. It's the interchanging of the ordered pair, where you see x you put y and vice versa. So that's what it means graphically, is a reflection in the line y equals x, and that's it. Now, I now want to talk about what the term relation is. Well, first of all, the word relation is a set of ordered pairs. Every graph is a relation. But there's a certain number of graphs that we want to talk about, or what are called functions. So what is a function? If I draw this line here, draw this curve, let's say y equals, and I'm using y not fx, y equals x squared. That is a function. And what's the word function mean? For one value of x, there is one value of y. Any value you take across here, for x, you'll get one y value. This was, say for argument's sake, is 1, then this gives, when x is 1, you get one y value. When x is 1.5, you get one y value, and so on. Minus 1, you get one y value. So that y equals x squared is called a function. Good. However, if you take a curve such as a circle, and let's take the unit circle, which is x squared plus y squared equals 1. In other words, the radius is equal to 1, and the centre is the origin. That is not a function. The function, see, if you put a line through here, vertically through there, at a value, say a half, for one value of x you get two values of y. So the circle, the way it's represented here, is not a function, it's a relation. And so it's very important to exactly what a function is. Now, what we did a minute ago is spoke about y equals e to the x, and that clearly is a function. For one value of x, there's one value of y. If I put a line through here, in other words, the line y equals x, and I drew the reflection in line y equals x, I found out this is y equals e to the x. I established this as y equals the log of x to the base e. This one here is also a function. In fact, it's the inverse function of this particular graph here. Y equals log x to the base e is the inverse of y equals e to the x, or vice versa. Y equals log x to the base e, the inverse of that is y equals e to the x. And the most important in mathematics, as I said earlier, you're going to do growth and decay. When you see an exponential, you also got to think of log, because they're interchangeable all the time. The definition of a log, if a to the x is equal to a number, then the log of that number to the base a is equal to x. That's the definition of a log, and clearly there's exponential and the interchangeable. I'll say that again. If a to the x is equal to n, a number, then the log of the number to the base a equals x. If we talk about the unit circle, that is the centre of the origin, radius 1, as in the diagram here, that's called an implicit function. Now they're words that are not used a great deal except at university, but you can make that y equals plus or minus the square root of 1 minus x squared. Simple arithmetic would give you that. And it's interesting that a lot of students don't know the term, like if you say what's the square root of 4, what is the square root of 4? The square root of 4 is 2. The definition of the square root of a squared is equal to the absolute value of a. Now I'm just putting that down because that has been asked in the HSC and I don't have time to go through it again. But the square root of 4 is not plus or minus 2, it's 2. If you have a look at it here, that top part of this curve, there's two parts of this circle, which they call a semicircle, is that, in other words, it's plus that, or y equals minus the square root of 1 minus x squared. Now this comes into harder sums later, as we'll try and finish up this lesson a little bit in a few minutes' time, but this is the top part of the semicircle here, and this is the bottom part. The plus, the square root of 1 minus x squared, if it's plus, is this part. So if you say y equals plus the square root of, let's say, 4, the answer is 2. And so that part there. If you're going to try and do anything with this circle, they might ask a question, what parts of that circle would make it a function? Well, you've got to take the top part or the bottom part. What parts of that circle, most of the circle, will make it a function? Now, it's no good doing this, say, here, to take an arc like that, because that is not a function. And so if you're going to make this x squared plus y squared equal to 1, the only way of doing that curve there would be to take that part, and that would be the function. And that would be the equation, the top part of the semicircle. Y equals the square root of 1 minus x squared. Take another example, just while we're talking about all this. If you took a parabola, what's the inverse of the parabola? Y equals x squared. What's the inverse of that parabola? X equals y squared. And the curve x equals y squared, if it's reflected in the line y equals x, clearly would be on its side, a parabola on its side. To make this, and what I referred to a minute ago as an explicit function, y equals plus or minus the square root of x. And if that part there, this part is y equals plus the square root of x, and the bottom part is y equals minus the square root of x. This arm here, if I draw the arm of that parabola, the arm looks like that, and that is y equals plus the square root of x. And that clearly is a function. If you take the whole card here, it's not a function. The original curve y equals x squared, I'll just draw it again maybe. The original curve y equals x squared is a function. The new curve, its inverse, is not a function. It is not an inverse function. And to take a part of that would give it an inverse. You'd take the bottom part, or you'd take the top part or the bottom part, the top sort of arc here, that part, or the bottom part. Now it's very important to notice this. When you have a curve, if you took y equals x cubed, and you said, does that curve, which is a function itself, does that function y equals x cubed have an inverse? Now that they use the term a horizontal line test. Now in simple terms it means this. If you go back to this curve here, for one value of x you get one value of y. Now if you look at that curve here, if you're going to change the ordered pair, you say to yourself, for one value of y in this one, when you do the inverse, it becomes the x values. In other words, the y values become the x values. So for one value of y, you end up getting one value of x. So this curve here, when it does what we did a minute ago, the inverse of y equals x cubed is x equals y cubed. That is a function. Now part 2 of this question is interesting. It's we had originally up here fx equals e to the x minus e to the minus x. We've shown that's an increasing function. You might ask, why did they ask whether it's an increasing function? Because if you think about it, if it's increasing function, for one y value, there is only one x value. It's not like that circle or that parabola that you had that comes down and is decreasing and then increasing. So if it's always increasing, that will always give, the inverse will always be a function. So it's something to think about. The next thing, and that's why that was, so you don't have to do anything to that curve at all as such, that it will give a inverse function. Now the next thing is show the equation of the function is given by that. Now it's fairly easy to say, okay, let y equal to e to the x minus e to the minus x. The inverse and write the word inverse down, is x equals e to the y minus e to the minus y, and that's the answer. The only difference from that is that instead of putting it in that, what we call possibly implicit form, we'd have to make y the subject. Most students understand you've got to make y the subject. And this is a bit of a trick. How do you make y the subject? This is the hardest part. Anybody can interchange the ordered pair. So you say, righto, we're going to make y the subject, make it e to the y, well, I put it's e to the y minus 1 over e to the y. Now, in that form there, multiply both sides by e to the y, and if I can just move up a bit, and you get e to the 2y minus 1. Now that's an equation, and to solve that equation, we'll make it e to the 2y minus, put that over the other side, minus 1 is equal to 0. Now, in that form there, that is a quadratic equation and in terms of e to the y. So what do you mean by that? Everyone's familiar with x squared minus 3x plus 2 equals 0. That's a quadratic equation. This is a quadratic equation too. You've seen it probably in e to the 2x minus 3 e to the x plus 2. If you're asked to solve that, you would solve that and find out what e to the x is. And I'm going to do the same thing here. What about x? We're going to solve this in terms of e to the y. X itself is regarded like a constant. And the only way I can solve that is not through direct factorisation, but we'll be using what they call the formula, the quadratic formula. And the quadratic formula is e to the 2y is equal to, is e to the y is equal to minus b, which in fact is b is minus x, plus or minus the square root of b squared, which is x squared, minus 4, a in this case is 1, by c is minus 1. So we get that form there, over 2a. So I'll put this down clearly, is x plus the square root of x squared plus 4 over 2, or e to the y is equal to x minus the square root of x squared plus 4 over 2. So there's the two forms. I'll just say this again, because I might have missed out on that, is we used in this form here, this particular equation, I'm saying is a quadratic equation, but we find in the unknown is e to the y. And this is the minus b, a is 1, c is equal to minus 1. So e to the y is x plus or minus square root of x squared, and putting the other values in using the quadratic formula, you get that result. Now clearly you can't have two forms for it in one equation. Now one of those is not correct. In other words, only one would give you the right result. Now clearly it is this one here. Why? Because the square root of x squared plus 4 I mentioned earlier is positive, and x squared plus 4 simplified is certainly going to be bigger than x. So if you take x minus a negative value, that's undefined. So with this part here you put this undefined. I hope I've gone fairly quickly with that. That's your answer. Now we haven't made y the subject, and one easy way is take the log of both sides. So if you take the log of e to the y to the base e is the log of all of this x plus the square root of x squared plus 4 over 2 to the base e, and the log of e to the y to the base, the log of e to the y to the base e is y, and the answer becomes the log of x plus the square root of x squared plus 4 over 2. And we have a look at the question now. That is the inverse. Now this fellow puts in here y equals such and such, or I put y equals there. This f to the minus 1x is a notation. So that's your new y equals that, which is the answer that I've just worked out here. Just want to draw the curve y equals sine x, and you would know that sine x goes through the origin, comes down here. So let's draw that part of the curve, and you've got the domain across here with the radians, and you get y equals y equals sine x, or that's part of it, and so forth. It's a continuous curve and leaps around and it goes for an infinite number of values of x to the domain. However, the range is only between -1 and 1. Now that's y equals sine to the -1x. I beg your pardon, y equals sine x. If you want the inverse of that, let's draw it on a different graph. The inverse would be the reflection in line y equals x, and the inverse is x equals sine y. And I didn't write that too well. I'll do that again. X equals sine y, and it has that effect. In other words, looks like a bit of a snake. It keeps going around. I haven't drawn it too well, but this part here is now. We'll put it if the y values are between -1 and x, they become the x values between -1 and x, and the range of values becomes all the radians here is pi over 2 and pi, etc. And this would be minus pi over 2. If you want to talk about the function, this of course is a relation. So the only way you can get a function is which might include the origin, is this part of the curve here. And if you do that, that part of the curve is actually the curve of y equals sine to the -1x. Now sine to the -1 of x, y is, and I said this just a minute ago, this is between -1 and 1, and this is between minus pi over 2 and pi over 2. Always label your graph, and that's between y and x, and that's the curve there. And if you put it down here, the range, and always use the word domain first, domain is between -1 and 1, and the range of values, as you can see from the curve, is minus pi over 2 to pi over 2. So that's the curve of the inverse. Now, y equals sine to the -1, I said y equals sine to the -1x. Sine to the -1x, or y, is an angle. It's an angle in radians. And we've seen that just from the previous and the definition. So if you were given a sum like this, what is the sine to the -1 of a half? Now to answer the question there, sine to the -1 of a half, you just said it's an angle in radians. Let's call it theta. Now you do the interchanging. I said before, if y equals sine to the -1x, x equals sine y. That's where we started from. And that gets right back to the definition and the reflection and the line y equals x and so on. So we do the interchanging here. Sine to the -1 of a half is theta, therefore you can say theta is equal to sine to the -1 of a half. Now sine to the -1 of a half is a trig ratio, and you got 1 over 2, and so this clearly would be root 3. And sine to the -1 of a half, or you would know, normally they put it the other way around, they draw it this way, and they put theta here, and you put root 3 and 2 and 1, whatever. And you know that this angle here, of course, is pi over 6. Now you might say, well, sine to the -1 of a half, sine to the -1 of a half, theta equals sine to the -1 of a half. To work that out, well, you might say there are lots of other angles. Why are there only one angle? Why is there only one angle? Why is there only one result? Because it comes back to inverse trig function. It comes back to inverse. If you looked at the curve, the original curve, which we said y equals sine to the -1 x, for one value of x, there is one value of y. So in this part here, there's one value of x gives one value of y. For sine to the -1 of a half, x is a half, there is only one y value. There's none others, that's it. I'd like to give an example of question 5C, the HSC question in 2007. Now this is a little bit of a more interesting, just following on from the recent discussion about sine to the -1x as an angle. This sum here, as you can see, there are two equations, and it's like simultaneous equations. You've got x and y. If you've got two equations which you're familiar with, they call them simultaneous equations. If you have that, and solve that particular equation there, x minus y equals 3 and x plus y, well, clearly they can do that in year 9 or year 8 even. You eliminate one of the unknowns, and we'll do exactly the same principle here. So what we do in this sum here, if you can see that if I add both those equations together, and I call it equation 1, I'm trying to do this a little bit quickly, but if you add both those equations 1, so you add equations 1 and 2. Don't forget, this is a question 5, by the way. Add equations 1 and 2. You end up, they cancel out, and you end up getting 4 sine to the minus 1x is equal to, that plus that is equal to, pi over 3 plus 2 pi over 3 is 3 pi over 3, which is that, and so we end up getting sine to the minus x is pi over 4. Now sine to the minus 1x, sine to the minus 1x is an angle in radians, which we've found out. And now I use the interchanging. Don't forget, we can make that, therefore, x is equal to sine of pi over 4. And you've got to triangle, your right angle triangle, or you're supposed to know that this is the answer for x in this relationship here. X clearly equals 1 over root 2. Now, that's the x value. And just to go over it again very quickly, you've got what I refer to, two equations. And even in the exam for the students, the examiner used the word simultaneous equations. And as soon as you see the word simultaneous equations, you've got to think in where you come from. You think in terms of what did you do in year 8, year 9? You solve those. And that's what the question is. Find the exact value of x and y. So this is 3 marks and it's of question 5. So in this particular sum here, I found out that x equals 1 over root 2. Some students might still be thinking, in that particular equation here, why can't you get multiple values of x? Well, we get back to, we're talking about, in this sum, inverse trig functions. For one value of x, there's only one value of y. Okay, so now, if x equals this particular value here, which is correct, we can put the x back into one of these equations, so we get the sine to the minus 1 of 1 over root 2. Might just go a little bit clearly here. Might make this make it a little bit easier. Sine to the minus 1, I'll write it down so you can see this a bit easier. Sine to the minus 1x plus a half cos to the minus 1 of y is equal to pi over 3. Now, we just found out from here that sine to the minus 1x is pi over 4, so we don't need to work anything out. So we'll put pi over 4 then. That's fairly easy. I'm using that information there. And that's a half cos to the minus 1 of y is equal to pi over 3. Now here, you take pi over 4 from both sides. This side over here is 3 pi over 12. I think we multiplied top and bottom by 4 rather. 4 pi over 12, take away 3 pi over 12 becomes pi over 12, I think. And that's a half cos to the minus 1 of y. Multiply both sides by, in this sum here, multiply both sides by 2, and you get pi over 6. And you come back again, and I'm jumping around but you've said this root 3, 2, 1, this trig relationship, root 3, 2, 1. Now you know that that's 30 or pi over 6, and this is pi over 3. So what is y equals cos of pi over 6? And what's the cos of pi over 6? Is root 3 over 2. So the answer for that sum there, y equals root 3 over 2. So this is a 3-mark sum, and it's using the definition of what the inverse sine and cos was.